Straight in, the first section is analytical geometry, and the very first question asks us to find the length of line AC. So we're just going to use our distance formula as it's provided. Remember, the distance formula is just the difference between the x values of 2 points squared added to the difference between the y values of those same 2 points squared. Right, so here from A to C, the distance between on the sort of x coordinates is actually 19, right? So it's going to be 19 squared. That's either minus 13 minus 6 or 6 minus 13. Either way we'll get 19 because when we square it, even if it's negative 19, it's still going to be 19 squared. The change in the y values is actually just 2. So it's either 3 minus 1 or 1 minus 3. When we square it, we get 2 squared. Right, so we get a final answer here of the square root of 365. The question did ask for answers to one decimal place, and that's 19,1. Right, so the next question says determine the equation of a circle which with center C, which has the x-axis as a tangent. So it's going to be a circle somewhere kind of here, like that. We know the center is negative 13, 3. And the radius is clearly going to be 3. Right, so our standard form for the equation of a circle is x minus the y coordinate of the center. So it's actually going to be x plus 13 all squared plus y minus 3 all squared. And then that will equal our radius squared, which will be 3 squared. So it'll be 9. Okay, determine the coordinates of point D if A, B, C, D is a parallelogram. Let's just have a look at this. Okay, just going to rub out this circle. A, B, C, D. Okay, so let's just take a look at how that might look. It looks to me A, B, C, D. It looks to me like D might be somewhere kind of over here. All right. The important thing is that as we move, if we picture kind of almost like a vector, the opposite sides of a parallelogram are not only equal, but they're also parallel. So what happens as we move from point B to point C, so it's rather a bold highlighter, from B to C, the same must happen as we move from A to D. All right, and I've changed my mind a little bit about where point D might be. Okay, so as we move, that's because this is not only parallel, but also equal in length. So as we move from B to C, the x value decreases by 8, so it must decrease by 8 as we move from A to D, from 6 to negative 2. The y value decreases only by 2, so in fact this will be negative 2, negative 1. Right, you might well try and just see, and we'll get exactly the same result if we were to say, right, as we move from B to A, the same thing must happen as we move from C to D, right? Because again, these are parallel and equal in length. So as we move from B to A, let's go from A to B, the x value decreases by 11. Sorry, as we move from B to A, the x value increases by 11. So from minus 13, if we increase by 11, we get minus 2. And the y value decreases by 4. And if the y value decreases by 4 from 3, it goes to minus 1. So D is the point, negative 2, negative 1. Negative 2, negative 1. Let's just fill that in. Right. The next question says determine the equation of the perpendicular of BC. Right, now BC, just losing my way a little bit here. Determine the equation of the perpendicular of bisector of BC. Okay, so the first thing we need to do is we need to work out the gradient of BC. Right, BC is a line that's sloping uphill. Remember, we're going to use our gradient formula, which is our change in y values divided by our change in x values. And so for BC, we actually get a gradient of minus 4. So if we get a gradient of 1 quarter for BC. Right, it's risen 2 in the time that it's run across 8. So the perpendicular gradient, remember gradients that are perpendicular, multiply together to give -1. All right, another way of thinking about it, if we change the sign and turn our gradient over, we get -4, and that's the perpendicular gradient. But now it's not only perpendicular, it's also a bisector of BC. It needs to go through the midpoint of BC. So remember, our midpoint formula also gets provided. Our midpoint formula is just the average of the x-coordinates of the endpoints. So in other words, we add them together and divide by 2, and the same with the y values. So y1 plus y2 over 2. All right, if we put point B and point C into there, we actually get that the midpoint is -9, 4. Right, so now we have a gradient and we have a point. All right, and we can use either form for our straight line. We can use y equals mx plus c. My preference is actually this formula, y minus y1 is the gradient x minus x1, where my point that I'm going to put in is x1, y1. So in other words, y minus the y value is the gradient, -4, x minus the x value. And because it's -9, it actually becomes +9. Okay, and we get a final answer of y equals -4x minus 32. Okay, right. Next up, we're going to use the fact that the angle of inclination of AB is 160 degrees to determine the size of obtuse angle CBA. Right, I'm just going to draw in basically what we've got here. We've got B over here, we've got A over here, and we are told that the angle of inclination of A, remember the angle of inclination is from the positive horizontal axis going around anti-clockwise. So we're told that this is 160 degrees. This point over here is C. We've already worked out the gradient of BC to be 1/4. Now, the question, the angle we're trying to find is this angle over here. All right. What we are able to find now is we're able to find this angle over here. I'm going to call it alpha. All right. So the tan of alpha is actually 1/4, which means that alpha is going to be shift tan, undo tan of 1/4, and that comes to 14 degrees. Right, now what we know is that this angle here, 160 degrees, is the angle we're trying to find, which is CBA, plus alpha, which is 14 degrees. And the reason for that is that the exterior angle of a triangle is equal to the opposite interior angle. So exterior angle of, sorry, not the opposite interior angle, the opposite interior angles added together. So in fact, a CBA is actually going to be 160 minus 14 degrees. All right, and that comes to 144 degrees. Okay, the next question asks for a point which is 1/4 of the way between 2 points. Now one of the things you could do, right, if you knew point A and you knew point B, you could find the midpoint using your midpoint formula, and then you could find the midpoint of from here to here, and that would give us a distance 1/4 of the way. However, I want to show you a little kind of method which will work for any fraction of down a line. All right, so the total change on my x value as I move from -2, 0 to 6, 16, the total move here is actually 8. All right, and I want to go 1/4 of 8. Now 1/4 of 8 is 2. So in fact, I want to add 2 to -2, and that will take me to this point over here, 0 something. All right, I want to show you, and I'm just going to change pen color, which I hope will be helpful. the amount that I've risen when I move from point A to point B is 16. Okay, so this is definitely not drawn neatly to scale. And a quarter of 16 is actually equal to 4. So I want to rise 4, and my y value of the point there will 4 will be 0. Well, the point will be 0, 4. Okay, that will work for any kind of fraction. So you can work out 1/5 of the way along a line, 2/5 of the way along a line, etc. Right, let's turn over and see what's coming next. We've got this question over here, and it asks us for the equation of this circle. Right, now, what we don't know, we don't know the coordinates of m, but we do know that this is a tangent, so in fact, we know that this is perpendicular, which means that m must have an x value of 2. Right. We also know that if its y value is, say, y, right, then this distance and this distance must be the same. Both of them are radii. So we're going to make a little equation now, all right? The formula the distance AM is actually just equal to 0 minus y. It's just the change in the y values. All right? BM is actually the square root of 2 minus 4. I'm using my distance formula. Squared plus y minus 6 squared. Okay, and those two distances must be equal. In other words, negative y must be equal to the square root. Now this is 2 minus 4, it's negative 2, squared is 4, and this is y plus 6, all squared. What I'm going to do now is I'm going to square both sides. When I square both sides, and I'm doing that to get rid of the square root sign, I get y squared, and here I get 4 plus y plus 6, all squared. Okay, so this actually simplifies down about multiplied out. I actually get y squared plus 12y plus 36 plus 4, so plus 40, all right? And then over here I've got y squared. So in fact what I end up with is that 12y is negative 40. And so y is in fact negative 40 over 12. It actually simplifies to negative 10 over 3. We expected y to be negative. Remember, y is the value of that point. Right? And now, don't forget to actually finish off and answer the whole question. The equation of the circle is going to be x minus the x coordinate of the center squared plus y minus the y coordinate of the center squared. So it's y minus 10 over 3. So it's going to be y plus 10 over 3, all squared, right? And what we do need to do is we need to work out what our radius squared is going to be. Now, our radius is actually the size of this y value, basically, without its sign. So in other words, this radius is actually 10 over 3, as is this radius over here. And the square of the radius is what we need in our formula. So we get 100 over 9. Right, next up, the question asks us to find the equation of the tangent to the circle at B. Just so I've got it all on one screen, I'm just going to draw a little picture here. I know this point here is 2, negative 10 over 3. And I know this point over here, B, is 4, negative 6. So what I'm looking for is I'm looking for the equation of this tangent, and this is a fairly standard skill that we need to be able to do, right? And it relies on us knowing another piece of mathematics. Everything's connected to everything else, right? The radius and the tangent will be perpendicular. So I've got these 2 points. I can work out the gradient of OB. All right, let's do that. The gradient of OB is going to be the change in the y values, so negative 10 over 3, subtract 6, divided by the change in the x values, 2 minus 4. Right, we sort all of that out, and it actually comes to negative 4 over 3. Notice it's a negative gradient, it's going downhill. So now the gradient of the tangent will be the negative reciprocal of that. In other words, we're going to turn it over and change its sign. It's actually 3/4, right? And the reason that we're doing that is that the radius is perpendicular to the tangent. So now I have the gradient. I have the gradient of this red tangent line as 3/4. Notice it's a positive gradient. It's going uphill. And the last thing I'm going to do, again, I'm going to use, this time I'll use y equals mx plus c. All right, so y equals mx plus c. And I'm going to put in the gradient, which is 3/4. I'm going to put in the x value, which is 4, plus c, and I'm going to put in the y value, which is minus 6. So what I've done is I've substituted in this point b into this equation. The only thing I don't know now is c. On the left-hand side, I've got minus 6. 3/4 times 4 is actually just 3. So minus 6 equals 3 plus c. Subtract c from 3 from both sides, and I get c equals minus 9. And then don't forget to finally write down the final answer. Y equals m, which is the gradient, which is 3/4 x plus 9. Okay. Right, let's turn over and see what awaits us on the next page. And this one asks us to find the length of the tangent. All right. Now, if I could get the center of this circle by writing it in standard form, once again, I know that is perpendicular, right? And if I know the center O, then I can work out this distance using the distance formula. And if I've put this in standard form, I will know the radius. And then I can use Pythagoras in triangle OAB. Right, so let's do all of that. First up, let's put this thing in standard form. And it's a really straightforward thing to do. What we're going to do is we're going to try and write it as x something squared plus y something squared equals. Okay. Now, the first thing I do is I'm going to add 5 to both sides. So I've got that. Right. Now, remember that when we complete the square, whatever I put here is going to multiply with the x and then double. So I must not put minus 4 here. I must in fact put minus 2. When I square this out, I get x squared. I get minus 2x from the inners, another minus 2x from the outers. I also get a plus 4, which I didn't have. By writing it like this, I've destroyed the balance. Now, the way I'm going to fix that is I'm going to add 4 to the right-hand side. So by writing it like this, I've actually added 4, which wasn't on the left-hand side previously. We're going to do exactly the same with the y's. It's going to be y plus, I'm not going to put 8, I'm going to put 4. If I square out y plus 4 all squared, I get y squared, I get 8y, but I also get 16 that wasn't there, so I need to add 16 here. Right. So the upshot of all of this is that this circle in standard form is x minus 2 all squared plus y plus 4 all squared equals 25. Right. Now that means that this point over here is the center to negative 4, and the radius is the square root of 25, so the radius is in fact 5. Okay, next up, I can work out what OB squared is. Right, I'm going to work out what OB squared is using my distance formula, but I'm not going to square root it, okay? So remember, OB squared is just going to be the difference in the x values, 10 minus 2 squared, added to the difference in the y values, 6 minus 4, 6 plus 4 squared. Right, so OB squared, okay, notice I've squared both sides, and I'll explain why I've done that now. This is 8, so this is 64, and this is 10, so this is 100. So OB squared is 164. Right, now, OA squared is the radius, is 25. And now if we look at this, this is the hypotenuse. So we know that OA squared plus AB squared equals OB squared. And this is Pythagoras. Okay, so OA squared I know is 25. I don't know what AB squared is. I'm trying to find AB. And I know that OB squared is 164. So if I subtract 25 from both sides, I get 139. So AB squared is 139. And then the last thing I need to do is just square root both sides. And I get that AB is equal to the square root of 139. And that is around about 11,8 units. Okay, right. Then let's see what the next question is. Question 1.5. This is a new question. It says, a point C is that distance from the center of the circle. Does it lie inside or outside the circle? Right, so what we're going to do, once again, we're going to write this circle into standard form. This is something that we really need to get competent and quick and accurate with. Okay, so x minus 5. Remember, I'm going to halve that coefficient because when I square it out, it's going to double. When I square this out, I actually get x squared. I get minus 10x, but I get minus 5 squared, which is 25, added to the left-hand side. So to address the fact that I've added it to the left-hand side, I've got to add it to the right-hand side as well. I'm going to do exactly the same with the y's. Y plus 2 all squared. Now again, when I multiply this out, I get y squared, I get 4y, but I also get plus 4, which wasn't there, so I'm going to add in 4 here. What I've ended up with now is 20. All right, so I know the center of the circle, okay, and I know the radius. Okay, and I now know that this point C is 4,24 units from the center of the circle. Now the radius is actually going to be the square root of 20. And when we square root 20, we get about 4,5. It's actually 4,47. 4,47. Okay, now this point is less than a radius away. So in fact, what we actually know, the radius is 4,47. This point is actually less than that away from the center. It's only 4,24. We don't know exactly where it is. It doesn't really matter. But it's definitely inside the circle. All right. And if you wanted to give a reason, you could say it's inside, since the distance from the center is less than the radius. Okay, right, the next question asks us to find the size of this angle over here. And what we're going to do, we're going to use angles of inclination. So first up, I'm going to work out the gradient of this line. It's risen from minus 8 to 6, it's risen 14. And from negative 3 to 4, it's run across 7. The gradient of this line is 2. You might like to use your y minus y1, y1 minus y2 over x1 minus x2, but that is the gradient of that line. Now what I'm going to do whenever I'm dealing with angles of inclination, I like to actually put a horizontal line into the diagram somewhere. All right, and so there we have it. Now this angle over here, I'm going to call alpha. Okay, and the tan of alpha is equal to the angle of is equal to the gradient of the line. All right. So in other words, the tan of alpha is 2. That means that alpha is shift tan of 2, which is 63,4 degrees. Okay. Now, likewise, I can work out the angle of inclination of this line. Okay, and I'm going to call that beta. Now this line's got a gradient of negative 0,4. So I know that the tan of beta is negative 0,4. Now what I prefer to do here is I prefer to actually work out what my key angle is. Okay, so I'm going to undo tan of 0,4. Right, and I'm going to just bring up a calculator to do that. Shift tan of 0,4. Okay, I see my calculator is not in the right mode. I'm just going to put it into degree mode. Shift tan of 0,4. Right, and I get 21,8 degrees. Now this angle is clearly not 21,8 degrees. This angle over here is actually 21,8 degrees. Okay, so what I'm going to actually do is I'm going to go that beta is going to be 180 minus 21,8. 180 minus 21,8 degrees. Okay, and what I get is that I get the size of beta is 158,2 degrees. Now if I look at my diagram, I can see that theta is just the difference between beta and alpha. So theta is going to be 158,2 minus 63,4, and I get a final answer of 94,8 degrees. Okay, and that brings us to the end of the section on analytical geometry. Next up, we'll dive into trigonometry. Right, let's continue. So we're now looking at a trigonometry question, and we're told that tan is positive and sine is negative. Now there's only one quadrant where tan is positive and sine is negative, and that's in this third quadrant. Okay, so theta is measured around from there. Really, really important. This is not theta, that's not theta. It's the whole way around from there in an anti-clockwise direction. Right, and we know that tan is 12 over 5 is y over x. Remember, tan is y over x. You don't get provided that formula. So the way that must have arisen is for y, in fact, to be negative 12 in this quadrant, and for x to be negative 5. And when we divide those two, we actually get the value of positive 12 over 5. So here's theta. And now it asks us to find cos theta. All right. Now, obviously, for cos theta, cos is x over r. We don't know what r is at this stage. Okay, but we can work out r using Pythagoras. Okay, second time we've encountered Pythagoras just recently. Right, this distance as a distance is 12, and this distance as a distance is 5. So r squared is actually going to be 5 squared plus 12 squared. Using Pythagoras, r squared actually comes to 25 plus 144. It's actually 169, and we get r equals 13. So this radius here is 13, and cos of theta x over r, cos is actually going to be negative 5 over 13. We expected cos to be negative in this quadrant. Okay, then it says determine theta to 1 decimal place. And I want to show you here that in fact we can work out what I like to call a key angle. All right, it's not my answer. It's just a step in the process of finding the answer. And when I work out a key angle, I'm going to undo the trig ratios. I'm going to undo cos, but I'm not going to put in the negative. I'm going to undo cos of 5 over 13. Or I could undo tan of 12 over 5 as provided in the question. And I want to show you that both of those are going to give the same value. So let's have a look. When I undo, let's find the calculator. When I undo shift cos of 5 over 13, 5 over 13, I get about 67,4 degrees. When I undo tan, shift tan of 12 over 5, I get exactly the same number, 67,4 degrees. That is not the answer, it is the key, 67,4 degrees. The key to finding a key is that we do not put the negative value in. Now, the way I want to get into quadrant 3 is I want to go 180 plus my key. I'm only going to use the horizontal axis. So, in fact, theta is going to be 180 plus 67,4, or 247,4 degrees. 4 degrees. Okay. Right. A basic idea, but a really important one. Now, this question here says simplify without a calculator. So this is interesting because it's presumably going to involve some special angles and some reductions first up, I'm just going to remind us of this, all sine, tan, cos. This tells us which ratios are positive in which quadrants. Sine of 90 plus theta. Now, when we go sine of 90 plus theta, we end up in the second quadrant. So this is a positive value. But when I deviate off a vertical axis, right, so 90 or 270, then sine and cos change around. So in other words, instead of this being sine of 90 plus theta, it becomes cos of theta. Sine of 160, well, I'm in quadrant 2. Sine is positive in quadrant 2, and I'm going to get exactly the same as sine of 20. I just want to show you that we can write 160 as 180 minus 20. Sine of 100, okay, sine of 100 is actually in quadrant 3, in quadrant 2 as well. This is the same as sine of 90 plus 10. Now I'm getting a little bit nervous here because I'm getting 10s and 20s, and those aren't special angles. Cos of minus theta, all right, minus theta means we've just come a little bit clockwise. Cos off a horizontal axis, that's just exactly the same as cos of theta. And sine of 190, right, 190 we're in quadrant 3 by 10 degrees. So in other words, 180 plus 10. So when I do these reductions, and you could leave this step out and go straight to this step, this is going to be cos theta. This is going to be sine of 20. And on the denominator, I've got I've got cos of 10. I've got cos of theta. And I've got negative sine of 10. Okay, so remember that that's a multiplication, it's not a subtraction, okay? What I can do, because I've got multiplications on all of these, I can divide the top and the bottom by cos theta. So what I've now got is I've got sine 20 on the bottom, on the top, and I've got cos 10 sine 10 on the bottom. 20 is double 10. So what I'm going to do is I'm going to write sine 2 lots of 10, and I'm going to use my double angle formula. Okay, this is going to be over negative sine 10 cos 10. And remember, sine of two things is actually 2 sine 10 cos 10. And on the denominator, I've got negative sine 10 cos 10. Okay, I'm going to divide the numerator and the denominator by sine of 10. Notice I don't know what sine of 10 is, but it doesn't matter because it's going to divide out. I can do exactly the same with cos of 10. So I get 2 times 1, which is 2 on the top, and on the bottom I've got negative 1. My final answer to this question, negative 2. Okay, right, let's move on to question number 2.3. And this one says, and again, we're going to keep this first and foremost uppermost in our minds, all sine, tan, cos, sine of 208. Right, now this question involves 28 degrees. So sine of 208 is actually the same as sine of 180 plus 28. Now, if I go 180 plus 28, I'm ending up in quadrant 3. Sine is negative in quadrant 3, and it'll be the same as negative sine 28 degrees. It doesn't change to cos because I'm coming off a horizontal axis. Okay, so in fact I get negative k. Tan of 152, well, tan of 152 is actually, it's the same as tan of 180 minus 28. Notice I'm always trying to incorporate the 28. And that's in the second quadrant, and so I'm actually going to get negative tan 28. Now we've got a slight challenge because we know about sine of 28, we don't know about tan of 28. However, we can draw a little picture here. Because remember, sine is my y value over my r value, or my opposite over my hypotenuse. And I'm going to write sine of 28 as k over 1. So k goes here, that's the opposite, and 1 goes here, that's the hypotenuse. I can now use Pythagoras, a third time in this paper. That squared minus that squared is this squared. So this adjacent side is actually going to be root 1 minus k squared. Okay, and now tan, remember, is opposite over adjacent. So I'm going to get k over root 1 minus k squared. Okay, that's the answer to that one. Right, if we look at C, cos of 304 degrees. Now, cos of 304 degrees is actually the same as cos of 360 minus 56 degrees. I'm in quadrant 4 by 56 degrees. All right. So, in fact, and we know that cos is positive in quadrant 4, so this is exactly the same as cos of 56 degrees. Now, we don't know about 56 degrees, but we know about 28 degrees. So I'm going to go 2 lots of 28, which is 56. Now I need to choose one of my 3 cos formulas. And you'll remember that there's one that just involves sine, or sine squared. There's one that involves sine squared and cos squared. And there's one that just involves cos squared. I know about sine of 28. So I'm going to go with the one that says 1 minus 2 sine squared 28 degrees. And remember, 28 degrees is k, so I get 1 minus 2k squared. Okay. The next question, 2.4, asks us to find the largest side in a triangle that looks like this. Okay, the largest angle. Now, the largest angle will always be opposite the largest side. So, in other words, I'm looking for this angle over here. Right. I actually like to learn a rearranged form, but let's suppose we haven't learned a rearranged form of the cos rule. Then remember, the cos rule says that any side squared is the other 2 sides that squared and added together minus twice the product of those 2 sides times by the cos of the angle in between them. Right, now there's only one variable left in here, and that's theta. So if I kind of rearrange all of this, I get cos of, sorry, let me just do that a bit slower. Let me not rush into it. I get 64 here. I get 25 here. I get 36 here. I get 2 times 5 is 10. I get 60. 60 cos theta. Right. Now this is in fact 25 plus 36 is in fact 61. I'm going to subtract 61 from both sides. I get 3 is negative 60 cos theta. I'm going to divide both sides by negative 60, and I get negative 1/20th is cos theta. Now I want to find the angle, all right, and it's an angle between 0 and 180, obviously, because it's in a triangle, but I'm getting the negative value for cos, so it's obviously an obtuse angle. What I'm going to do, as I've done every time when I solve a little trig equation, I'm going to find a key. And remember, the key to finding a key is I'm not going to put the negative into the calculator. So I'm going to go shift cos, all right, of 1/20th. Let's see what I get. Shift cos of a 20th. And I get 87 degrees. Now that's not the answer. That is the amount from a horizontal axis that I'm in that quadrant. So in fact, it's going to be 180. Theta is going to be 180 minus 87, 1. 180 minus 87, 1. And my final answer is 92.9 degrees. Okay. Right, the next question is looking at some trig graphs. And it's asking us to find the equations of these trig graphs. Now this first one, I'm hoping you're comfortable with, is clearly a sine graph, right? However, the amplitude has changed. And the reason we know the amplitude has changed, normally a sine graph maxes out at 1 and at -1. Now it's being stretched vertically, so 3 sine. However, normally a sine graph takes 360 degrees to do a cycle. It's now doing 2 cycles, 2 waves. So this is actually 3 sine 2 theta. This next one looks very much like a tan graph. However, the period has altered, and the reason we know the period has altered is because normally our asymptote would be at 90, now it's at 180. I'm only getting half as many tan graphs as usual, so tan of a half of theta, right? And the other thing is that this is actually normally tan of 90 over 2 would give us 45. Tan of 45 would normally give us 1. In other words, we'd expect the graph to be going uphill first. It's actually been reflected in the x-axis. So there's the equation of that one. Okay, the next one looks very much to me like a sine graph that has been moved down. Its overall height, the total height, is 2, amplitude of 1. So it hasn't been stretched, nor has the period changed. Okay, so this one, I'm just going with y equals sine theta minus 1. Okay, and then this last one over here looks very much like a cos graph. Okay, and it's hitting over here at 70 degrees. Now, normally a cos graph would hit the x-axis at 90 degrees. So the graph's actually been moved to the left by 20 degrees. Cos theta plus 20. But it is also, in fact, a sine graph that's been moved a whole lot to the, so this is a cos graph that's been moved 20 degrees to the left, right? It is also a sine graph that's been moved 70 degrees to the right. So in other words, another option, maybe not such an obvious option, y equals sine of theta minus 70 degrees. Okay. Right, let's see if we can prove this identity. Remember, the key thing when we try and prove an identity is we only work with one side at a time. So let's have a look. Now this one's not necessarily all that tricky, but just a reminder that the very worst thing you can do is to do nothing. So even if you just happen to know that tan of 2x is the same as sine of 2x over cos of 2x, you've already got yourself a mark. Cos of 2x. Okay, let's look at the left-hand side though. This here, we should recognize immediately, if we've taken the trouble to learn our identities, we should know that this is sine of 2x. Okay, now, so if we look at, this is looking very good. Now, I need this to be cos of 2x. And remember, cos of 2x has got 3 different kind of flavors, right? If you're wide awake, you will spot that this is actually a difference of 2 squares. Okay, so this is in fact cos 2x. Sorry, this is cos squared x. Sorry, this is cos squared x minus sine squared x multiplied, and as you write that down, you should say, oh, hang on, that's cos 2x multiplied by cos squared x plus sine squared x. Okay, and we know that cos squared x plus sine squared x is 1. So in fact, what we've now got is we've got sine 2x over cos squared x minus sine squared x, but we know that cos squared x minus sine squared x is cos 2x. And I could either say right-hand side, or I could say tan of 2x, and I could say equals left-hand side, in which case I don't actually need, equals right-hand side, in which case I don't actually need any of that. Okay, right, let's turn over. Our next question is solving some equations. And again, if you've learned your identities, then you will recognize this. This is a compound angle formula. This is actually sine of 3x plus 10 degrees. Okay, and we know that that's negative a half. Now this is a standard trig equation. And I'm looking for answers in quadrants 3 and 4 because sine being negative. The first thing I'm going to do is I'm going to find my key angle. And remember that the key to finding a key is don't put the negative in when we undo the ratio. So when I undo sine of a half, I get 30 degrees. And now my answers are in quadrant 3 and 4, and I only use my horizontal axis. So my two sort of standard answers are 180 plus 30 and 360 minus 30. There they are. Each of those can happen every 360 degrees. K, an integer, a whole number, positive, negative, or 0. All right. Now, the last thing is that the angle wasn't actually x, it was 3x plus 10. So now what I'm going to do is I'm going to write those down, and I'm going to solve each of these generating general solutions for x. Okay, and so I'm going to subtract 10 from both sides, and then I'm going to divide through by 3. So the top one actually becomes 200 over 3 plus 120k. And the bottom one becomes 320 over 3 plus 120k. Okay, and that there's my general solution, and I can find as many specific solutions as I want if I'm given a domain. Just to make something clear here, this over here has caused the graph to have a smaller period, to have more answers. And notice that this is what's going to give us more answers. Instead of adding 360 multiple times, we're adding 120 multiple times. It makes sense. It always makes sense. Okay, the next one, an interesting one, because what we've got is we've got tan equal to tan. And I just want to show you something here, that if we've got, for example, tan, I'm going to do something much simpler. I'm going to do like tan of theta equals tan of 10. Then, and I'm going to picture this little picture here. The one obvious answer is that theta equals 10. But the other possibility is that theta, because remember tan is positive in these two quadrants. The other possibility is that theta is actually 180 plus 10 plus 360k. And what we know, in fact, with tan, this one's 10 and this is, well, the one's 190. What we can actually do with tan is we can just take one of our answers and add 180k. So what I'm going to do over here is I'm just going to say these angles are equal. All right, plus 180k. Sorry, not 360, plus 180k. Right, and so I get negative 3x is negative 20 degrees plus 180k. And if I divide through by 3, I get x is 20 over 3 plus 60, I'm dividing by negative 3. So in fact, it's going to be minus 60k. And don't forget, whenever we do a general solution, that we must say k is an integer. Okay, right. Onwards and upwards, we're going to get into some solution of triangles. All right. So we are told the size of the area of this front face of this three-dimensional shape. That area is there, 2k squared sine theta cos theta. We also know that PQ is k, and we know that PM is twice as big as PQ. So in fact, PM is actually 2k. Right, and then it says prove that MPQ is 2 theta. This angle over here, that it's 2 theta. Okay. Now, this is a typical question in the sense that we've got the area of this triangle, right? And remember, we know the formula for the area of a triangle, and the formula for the area of the triangle is going to be 2k times, so it's going to be a half times by k times by 2k. All right, so I'm using this side, this angle, and this side. And this angle is MPQ, so sine of MPQ but I know that, sine of MPQ, I know that that actually equals 2k squared sine theta cos theta. Okay, so on the left hand side, the half and the 2, that just becomes k squared. So this is the answer to A, by the way. All right, that's going to become k squared sine of MPQ. And on the bottom here, I've actually got k squared as well. So I can divide out k squared on both sides. And here I've got 2 sine theta cos theta. Now, again, if you've learned your identities, then you will know that 2 sine theta cos theta is just sine 2 theta. So I know that sine of MPQ is equal to the sine of 2 theta. And if I undo sine on both sides, I get that MPQ is 2 theta. Okay, now the next and last thing that I've got to do is I've got to find an expression for MQ. Okay, for MQ. Now if I look at what I've got here, I can use, I know, so I can use the cos rule, right? Because I now know 2 sides and an included angle. So MQ, all right, MQ squared is actually going to be k squared plus 2k squared minus k times 2k times by the cos of MPQ. But I've just proved that MPQ is 2 theta. So in fact, MQ squared is actually going to be k squared plus 4k squared minus 2k squared cos of 2 theta. Now let's have a look at what we are being asked to show. This is the answer to question B. I'm just writing it so I can see here. All right. I'm trying to show that it's got an expression only in terms of sine squared theta. If you've learned your identities, you will know that there are 3 different possibilities for cos 2 theta. One of them involves only cos squareds, so in other words 2 cos squared theta minus 1. One of them involves cos squared and sine squared. It's actually cos squared minus sine squared. And the last one involves only sine squared, and that's the one I'm going to use. And I'm guided by looking at what the answer is requiring. So cos 2 theta is actually 1 minus 2 sine squared theta. Okay, and I'm nearly there now because MQ squared is actually going to be 5k squared minus, sorry, this is not 2k squared, sorry, this is 4k squared. So I get 5k squared minus 4k squared, I get k squared. And here I get plus 8 k squared sine squared theta. And the last thing I need to do is factor out a k squared. So I get k squared 1 plus 8 sine squared theta. And this is not MQ, it's MQ squared. So the last thing I'm going to do is I'm going to square root both sides. The 1 plus 8 sine squared theta is going to stay under the root sign. And the k squared is going to come outside the root sign and just become k. And there we have it. Okay, right. Not easy, but not too bad if one's done lots of practice and if one's learned one's rules and identities. Okay, then the last question in the trigonometry is this one. Another kind of 3D problem. Let's just have a look at it. It's asking us to show that the height of the tower is given by that. Right, now this is a typical 3D question, and what we've got a bridge. All right, in this triangle over here, triangle number 1, triangle ADB, we do not have enough information to get the height of the tower. All we've got is a right angle and one angle. However, and these questions often work like this line over here, I'm going to call a bridge, ibilocho, okay? This line, this green line AB, actually occurs in the triangle number 1, but it also occurs in triangle number 2, the triangle that's on the floor in the horizontal plane. So what I'm going to do is I'm going to get an expression for AB, okay, in terms of using the bottom triangle. Right, so I'm going to do this over here just so I can see exactly what I'm doing. So AB over the sine of alpha is going to be D over the sine of this angle ABC. All right, but ABC, all right, is actually 180 minus 2 alpha. Right, and that is because of the angles of triangle ABC. Okay, so instead of writing ABC here, I'm going to go 180 minus 2 alpha. Right, AB, what I'm going to do is I'm going to multiply both sides by sine alpha, so I get D sine alpha. On the denominator, I've actually got sine of 180 minus 2 alpha. That's a reduction formula. We're into quadrant 2, or for horizontal axis. Sine of 180 minus 2 alpha is just sine of 2 alpha. This can actually simplify somewhat because I know my compound angle, my double angle formula for sine. Sine 2 alpha is actually 2 sine alpha cos alpha. Okay, these can divide out, and I get D over 2 cos alpha. Okay, now that is my ibilocho, my bridge. So now in triangle number 1, which trig ratio would involve the opposite and the adjacent? And in fact it would be tan. So the tan of alpha will actually be dB over AB. So in fact dB will be AB times the tan of alpha. Okay, and now AB is D over 2 cos alpha, and tan alpha I can write as sine alpha over cos alpha. Okay, and when I simplify this and just multiply the tops and bottoms of these two fractions, so multiply the tops, D sine alpha, and the denominator 2 cos squared alpha. Alright, and there it is, and that's exactly what I was asked to show. Reasonably tricky one, but just using all the rules that we need to know and learn. Okay, that brings us to the end of the trigonometry, and we're going to dive straight into the geometry. This first question is just asking us to find some values. It's saying we don't need to give any reasons. This one, though, is in fact the proportional intercept theorem. So as long as I take two corresponding bits and divide them in the same way, if I go x over 8, 3, that will be the same as taking 3, 3 over 6, 8. It's actually line parallel to one side of a triangle, and if I was giving reasons, I would say parallel lines as well. I'd say which lines are parallel, but we haven't actually had them labeled here. What I'm going to do now is I'm going to multiply both sides by 8, 3. So I get 3, 3 over 6, 8 multiplied by 8, 3. Okay, and I get basically 4 centimeters. It's actually 4,03 centimeters, and that's to one. So to one decimal place, it's actually 4,0 centimeters. Okay, this next one asks us to find the size of x. All right, and what we can do here is we can work out this. This is going to be 360 minus 29. Oh, sorry, 360 minus 129. Okay, and so in fact and x is going to be half of that. So in fact, x is actually going to be 360 minus 129. 360 minus 129 is actually the kind of blue piece, all right? And then I need to divide by 2, right? And I get 115,5 degrees. Why am I dividing by 2? I'm dividing it by 2 because of angle at center. Another way of working this out is to work out this angle over here. If this is 129, this will be half of 129, angle at center. Helpful if you turn the diagram upside down to see that. All right, it's actually 54,5 degrees. And then I can use the cyclic quad, the opposite angles of a cyclic quad, and subtract them. Sorry, it's actually not 54, it's 64,5 degrees. Okay, and then the supplement of 64,5 is 115,5. Okay, this next question involves two similar shapes, right? And if we've got similar shapes and their sides are in the ratio 3:1 as they are, 18:6 is 3:1, that's the sides. To get the ratio of the areas, we square the ratio of the sides. So in other words, this will be 3 squared as to 1 squared. So in other words, the areas are in the ratio 3 squared as to 1 squared. The areas are actually in the ratio 9 as to 1. What that means is that this one is 9 times bigger than this one. So in other words, 9 times 53 would give us x. Right? And so in fact, x is 477 units squared. It's 9 times bigger than the small triangle. Okay. Similar triangles have areas that are in the ratio equal to the square of the ratio of their sides. I said triangles, it's actually true for any similar shapes. Right, this next one is a piece of bookwork. It's something we can easily learn. What we're trying to show is that this angle over here is equal to this angle over here. Let's just put some more labels on here. Let's just call that GCB. So we are trying to prove that DCB, and in fact what we can do, we can label angles as we like. So I'm going to call that, we're trying to prove that C2 is equal to angle E. We are trying to prove the tan chord theorem. Okay, now what we do, and this is something we need to learn, we make a construction of a diameter here. So in other words, we join that up. All right, and we also join in that. Okay, now I'm going to call this F. So what we'd write here is that we've constructed diameter CF, and then we've joined FD. Right, now what we can see is that FCB equals 90 degrees. Okay, what I'm going to do is I'm going to let C2 equal x. Now the reason FCB is 90 degrees is radius perpendicular to tangent. We've seen that already in the analytical geometry of this paper. So if this is x and this whole thing is 90, then I know that in fact C1, sorry, I'm not going to call that C1, I'm going to call this C1. I'm going to move this little one here to there. All right, so C1 is not, let's go scratch that, sorry. C1 is 90 degrees minus x. C1 however, FDC is 90 degrees, and that's because of angle in a semicircle. So if this is 90 degrees, and this is 90 minus x, so this is x, this is 90 minus x, this is 90. From angles of a triangle, we get that angle F must be x. So therefore angle F equals x. Angles of triangle, and it's actually angles of triangle CFD. Right, but angle E is also equal to x, and that's because of angles in the same segment. Right, so therefore C2 is equal to E. Okay, and that's pretty straightforward because you can actually just learn that. Right, next up we're gonna dive into question 3.3. So we've got this diagram. I'm just going to zoom out a little bit here just so I can see the whole diagram. Part A, and I'm going to answer the questions up here. Part A asks us to find BCD. BCD. Now, this is a diameter, so BCD is actually going to be 90 degrees. Angle in semicircle. Angle in semicircle. Okay, then part B asks us to find angle A1. Right, this angle over here. Okay, and we've just worked out that this is 90 degrees. Right, what we know is that OB equals OA. They are called radii. Right, in other words, that's equal to that. And so therefore, A1 is actually going to be the same as B1. It's going to be 38 degrees. And the reason for this is angles opposite equal sides. Okay, C asks us for angle O2. Now O2 is an exterior angle of triangle OBA. So angles O2 is actually going to be 38 plus 38. It's going to be 76 degrees, and the reason is exterior angle of triangle. Okay, and then D asks us to find angle C4. Right, C4 is this angle over here, and it is made between this tangent and this chord. And this chord, in fact, makes an angle over here. So the theorem that we've just proved, the tan chord theorem, C4 will be the same as B2. C4 will, in fact, be 33 degrees. And the reason for that, tan chord theorem. Okay. And I think that might be the end of that question. We're just going to turn over and check. Yes, indeed it is. Right, so let's move on to question, I called it 3.3, but it's actually, should be 3.4, but anyway, it's the next question. Now, this question involves proportional intercept theorem. It might also involve triangles that have got a shared height. The first thing we're going to do is we're going to mark in the ratio that we are given. So CF to FB is 3:2. So I'm going to call this 3P, and I'm going to call this 2P. Okay, they're not 3 and 2, but they are in that ratio. The first question asks us to find AD to DC. Now AD to DC is going to be exactly the same as BF to FC. And the reason being, it's line parallel to one side of a triangle. It's our proportional intercept theorem. And the parallel lines that I'm using are DF parallel to AB. Okay, so it's actually going to be this, it's going to be 2P is to 3P. It's actually going to be 2 as to 3. Okay, the next one asks us for the area of triangle AFD to the area of triangle DFC. So what we're talking about here, we're talking about this triangle to this triangle. Now those two triangles share a height. Right, might not be obvious to you, but if you turn the diagram around so that AC is the base, then you'll see that they have the same height. Triangles that share a height have their areas in the same ratio as their bases. So in fact, we've just worked out the ratio of the bases is 2 is to 3. So the answer here is just going to be exactly the same. It's going to be 2 is to 3, and the reason is shared height. Okay, the next one asks us for EF to FB. Now this is a little trickier. I'm actually going to answer it up here so that I can just see the diagram as I answer it. So I'm just going to make this eraser a little bit larger. Okay, right. So that's what we've got. Okay, now I know that this piece here is 2p and that piece here is 3p. Now this question involves EF to FB. What I do know, right, is that I know that AD, so this is the answer to question C, AD to DC is going to be the same as BF to, it's going to be the same, yeah. We already know that AD to DC is actually 2 is to 3. So what I'm going to do here is I'm going to put, for example, 2m and 3m. All right, that's coming from part A. Now I know that AD to DC is actually also the same as F it's the same as FE, so I'm using these parallel lines. Maybe it'll just be helpful if I highlight that. I'm using this parallel line here and this parallel line. AD to DC is the same as FE to EC. Okay. But I know that AD to DC is 2 is to 3. Right, don't forget to put a reason for this. This is again the proportional intercept theorem. The difference is that I'm now using these lines, AF parallel to DE. Okay, so I now am going to write some lengths on here. I'm going to say 2 as to 3. So I'm going to go maybe 2G and 3G. Now, if we look at what this question is asking us for, it's actually asking us for this piece, asking us for EF to FB. EF to FB, the kind of the blue piece to the red piece. Now the problem that I've got is that I know EF in terms of G and I know FB in terms of P. However, the little trick that I know, or that I can bring to bear here now, is that I have got the length of FC. I know that this is 3P, but I also know that it is, 3P. Sorry, this is just gone on the fritz here. I know that 3P is the same as 5G. 3P equals 5G. Right? And if 3P equals 5G, then P is actually 5G over 3. And FB is 2 lots of P. So in fact, FB is actually going to be 10 10g over 3. So now what I know is I actually know that this is 10g over 3 as well as being 2p. And now I've got EF and FB both in terms of g. So EF as to FB, I can write my ratio like that as a fraction or as a ratio, is going to be 2g over 10g over 3. What happens is the g's divide out. We get 2 over 10 over 3. Now 2 divided by 10 over 3 is the same as 2 times 3 over 10. It's 6 over 10. And 6 over 10 can simplify even further to 3 as to 5. Okay. Fairly tricky. I know people don't find this stuff all that easy. Right, let's look at this one. This one asks us to find the area of ADG, this little triangle over here, as to the entire triangle. Right, what we do know is that BF to FC is 1 as to 4. So for example, this might be 1p and this might be 4p. Right, what we also know is that triangle ADG is similar to triangle ABF. Right? And the reason for that similarity is angle, angle, angle. We've got a common angle up at the top here. We've got a corresponding angle there and a corresponding angle there. Okay. Now, what we also know is that AD to DB is 1 is to 2. So this is, for example, 1m and DB is 2m. Now, if we look at the ratio of the sides of these two similar triangles, they're actually 1 as to 3. All right? So the area of the big triangle ABF, that area divided by the little triangle ADG, that is actually going to be 9 as to 1. All right. I'm actually going to write it as 3 as to 1 squared. It's actually going to be 9 as to 1. Okay, all right. So what I can, and the reason for that is because we've got similar triangles. And if triangles are similar and their sides are on the ratio 1 as to 3, their areas are on the ratio 1 is to 3 squared, or in this case 3 is to 1 and 3 squared is to 1. Okay, so what I'm going to do now is I'm going to let triangle, the little triangle there, I'm going to let it have an area, this little one at the top. I'm going to let its area be A, 1A. Now that means that the whole triangle ABF is going to be 9 times bigger. That's actually going to be 9a. Right. Now, the last thing is that these two triangles, and I'm just going to highlight them for us, this green triangle and the entire triangle. So I'm now talking about the big triangle ABC. What do they share? They share a height. And because they share a height, their areas will be in the ratio of their bases. So in other words, this as to the entire thing, so if I take a, let's just do it like this, let's say triangle ABF as to triangle ABC, that will be the ratio of their bases. So it'll be 1p as to 5p. 1p as to 5p, it's just 1 as to 5. 1 as to 5. So what that means is that in fact ABC is 5 times bigger than this green triangle And the green triangle we said is 9a. All right. So therefore, right, and so the reason for this is shared height. Okay, so therefore ABC is actually 5 times ABF. Therefore ABC, triangle ABC's area is actually 5 times ABF. But we've already said that ABF is actually 9A, so it's actually 45A. And so now the ratio of the tiny little triangle at the top, which is 1A, as to the entire thing is going to be 1A as to 45A. So triangle ADG over the whole triangle ABC is going to be 1A as to 45A. The A's can divide out and I get a final answer of 1 as to 45. Okay, not easy, in fact quite challenging, but not too many ideas, really just similarity and shared height. Okay, and that brings us on to our very last question, which is a circle geometry question. The first thing we've got to do is we've got to prove that we've got a cyclic quad. We're trying to prove that AOCD is cyclic. Now, AOCD is here. Sorry. AOCD. Okay, I'm not doing this very well. AOCD. Right. Remember that we've got a couple of ways of proving cyclic quads. In fact, we've got 3. Right? We can prove the opposite angle supplementary. We can prove that the exterior angle equals the opposite interior angle. And we can also use the converse of angles in the same segment. And in fact, that is what we're going to do with this one. Because what I know, this is a diameter, so this is 90 degrees. And if this is 90 degrees, C1 and C2, then this one here must be 90 degrees. And because these two are equal, it must be a cyclic quad. All right, so I'm going to write all of that down. Okay. Angle ACB is 90 degrees. Angle in semicircle. Therefore, C3 equals 90 degrees. All right, angles on a straight line. Therefore, C3 equals O3. Now, I don't need to give a reason for that because I've shown that they're both 90 degrees. And so, therefore, the shape AOCD is a cyclic quad. And the reason is converse angles in same segment. Okay, that's part A. Part B says prove that C2 is D1. Right, now C2, if we look at where C2 is over here. Okay, C2 will in fact equal that one there. And it will equal that one there because they are angles opposite equal sides with our radii. But A2 will equal D1 because of the cyclic quad that we proved up above. Right, so I'm going to write this one down. I'm going to write this one down over here. This is B. All right. OC equals OA. Radii. Therefore, C2 equals A2. Angles opposite equal sides. But, quadri, but A2 equals D1. Right, and the reason A2 equals D1 is that they are angles in the same segment in the cyclic quad. And because C2 equals A2 and A2 equals D1, therefore C2 equals D1. Okay, now the next question asks us to prove some similar triangles. It asks us to prove that this triangle over here, OCE, this little red triangle, is similar to ODC. Now, ODC is in fact this bigger triangle. So we're talking about the little sort of red triangle, and we're talking about this bigger green triangle. Okay, and this geometry very often builds on itself, and this certainly does over here. What I know is that I know that C2, so this is my answer to question C, C2 is equal to D1. All right, and that has been proved higher up. So I've got one angle so far. The next angle that I know that is true for both of them, that is equal in both of them, is that angle O2 is common. Right, it's a shared angle, common or shared. And so therefore the third angle in the triangle, which in the little red triangle is E1, that must equal the third angle in the big green triangle, which is OCD. All right, and that's just third angle of triangle. So what I've got is I've got three angles equal. So therefore triangle OCE is similar to triangle ODC. And the reason for that is angle, angle, angle. Okay, and then the very last question that we're going to look at, question D. All right, I'm just going to go back to a red pen here. But question D, prove that OEOD is OC squared. I'm going to try and pull a ratio out of here. I know that OE, if I take OE from the first triangle, divided by OC, that will be the same as if I take OC divided by OD. And the reason I can do that is I've got similar triangles. Okay, now if I cross multiply here, in other words, if I've got two fractions equal, the top of this one times the bottom of that one equals the top of that one times the bottom of that one, I get that OC squared equals OE OD. And that's what I was asked to prove. And that brings us to the end of this video of going over the paper. I hope it's been useful, and I wish you everything of the best for your exam on Monday. Nkulunkulu akubusise nonke.